Hello! Today's math lesson is brought to you by Walmart. We are the only store that's open, pretty much. So you have no choice but to come and buy some more. Because we are your neighborhood Walmart. Alright guys, welcome to Pre-Calculus today. We're gonna get to some actual calculus. Isn't that exciting? We're jumping ahead to chapter 11. Ooh, new stuff. Okay, chapter 11 is an introduction to calculus and what is calculus, some of what it's all about here. If you want to read the story of calculus and the need for it, I suggest it's very interesting. I'm not going to take the time to read it to you now, but it's on page 754 on the top of the page, so check that out if you are interested in this story of calculus here. All right, so in this lesson, we are going to tackle one of the main problems of calculus, which is something called figuring out instantaneous rate of change, okay? And so in order to do that, we're going to need to use limits, and we will be solving something called the tangent problem when we find instantaneous rate of change. All right, so let's start with something you guys are familiar with. Velocity. Ooh, do you see that car down there? Ooh, green car. Okay, so hopefully that isn't too distracting. All right, so average velocity. This is a little bit of physics type stuff. Velocity, of course, is another name for the speed of something. All right, so you figure out velocity by taking the change in position divided by the change in time. Okay, so you could write it with this delta notation here. Delta S over delta T, where S is the distance, okay? And here you could have, this is V subscript AVE, or actually I would probably do AVG for velocity average. Okay, so you could write it like this if you want to write it out the long ways. Change in distance divided by change in time. Okay, so anyways, there's a problem down here. Oops, it's kind of hiding. So anyhow, let's check it out here. An automobile travels 120 miles in 2 hours and 30 minutes. What is the average velocity of an entire 2.5 time interval? Okay, so we know the distance was 120 miles, okay? We know the time at 2.5 hours. So all we would have to do is divide the distance divided by the time, okay? So that's 48 miles per hour. Now, of course, you want to make sure the time is all in the same units, so you want to make sure to convert the 30 minutes to a decimal of 0.5. All right, so that's average velocity. Now, on the next slide, we're going to generalize it. So we're not just talking about velocity, we're talking about the average rate of change. Now, that could be rate of change of, say, a fluid filling up a swimming pool, okay, gallons per minute. It could be the rate of change of a virus spreading, okay, people per day. All right, so there's lots of applications to this. It's not just velocity and speed. All right, so basically the same formula, okay? Only we're just substituting S and T with Y and X, okay? Average rate of change of Y with respect to X on the interval A to B. Okay, so X is changing from A to B, and Y is changing from F of B or F of A to F of B. Okay, so you would subtract, and this is, I mean, you could be decreasing or increasing, and this formula would still work. So anyhow, F of B minus F of A over B minus A. And that's really similar to the slope formula, okay? Geometrically, this is the slope of the secant line through 2 points. Okay, so instead of writing like points x1, y1, we're writing points a, f of a, and b, f of b. So this is very similar to slope, okay? In fact, this is the same thing as the slope formula. Average rate of change is the slope, okay? Now there's something called a secant line, which we'll talk about it, but a secant line is just a line going through 2 points, all right? Now we're going to get into more calculus ideas here. Okay, so we can find the average rate of change by using the slope of a line, but what if we wanted to figure out the velocity at a particular point, at a particular instant? Like, what is the speed of the ball when it leaves the pitcher's hand? Okay, this is called instantaneous velocity. It's the instantaneous rate of change with respect to time. So it's like time is approaching zero. Okay, time is getting so small that it's like split second instantaneous. Okay, but we cannot actually make the time zero, and hence why we need to use limits here. Otherwise, you would be dividing by zero, which you can't do. All right, so we get really, really, really close to A, okay? And so, as the function gets close to L, the x values go really, really close to A, but you can't actually get to A, okay? So that's just the informal definition of the limit here. So right now, okay, the reason why we use limits is mainly to avoid division by zero, okay? You can get really, really, really close to zero without being zero, okay? And that's why we use limits. And there is an example too on page 755 and 756, which I'm going to bring up right now. Here is this example too. A ball rolls down a ramp so that its distance s from the top of the ramp after t seconds is t squared feet. Okay. What is the instantaneous velocity after 3 seconds? So the cool thing about this is you're modeling distance with a quadratic equation. Okay. Ooh, that's really big. Let's try this again. So the equation is s equals t squared. Okay, so that's the equation that you are modeling this ball rolling down the ramp. Okay, the speed is increasing as the distance is increasing as the time is increasing. Sorry. So what is the instantaneous velocity? Well, since we don't know how to do calculus yet, we can estimate it by taking smaller and smaller time intervals, okay? And using that formula, which is the average rate of change formula that is in the notes. Okay, so let me quickly flip back there for you. And that is the average rate of change formula right here, okay? And here the y value is the distance and the x value is the time to cover that distance. Okay, so let's look and see what the book did here. Flipping to the next page. All right. So from 3 seconds to 3.1 seconds, okay, we could figure out the speed by taking t squared, 3.1 squared, minus 3 squared, okay? So you're subtracting the two. So this is A is 3, and B is 3.1, okay? And then on the bottom, the time difference would be 0.1, so the speed is 6.1 feet per second between 3 and 3.1. Now, if we make it smaller, the interval smaller, and only go 5/100th of a second instead of 1/10 of a second, our speed for this instant would become 6.05 feet per second. Okay? Now, which leads you to believe that as we continually make it smaller and smaller and smaller, guess what our speed ends up being? Okay? We can take the limit here, okay, as our time difference approaches 0. So as t approaches 3, okay, our interval is from 3 to 3 essentially. So you would have a division of 0 if you were to do 3 minus 3, but we're doing the limit here. Okay? And what you can do is actually factor the numerator, and then the factor t minus 3 will cancel out with the denominator, and then you're just left with t plus 3 here, okay? Now to actually figure out what the limit as t approaches 3 of t plus 3 is, all you do is you substitute that 3 in place of the t, so you have 3 plus 3, which is 6. Isn't that cool? So the instantaneous velocity is 6 feet per second, and we determined that with a limit here. All right, so let's go back to the notes here. So let's take a look at a connection to this graphically. All right, so tangent lines are what instantaneous velocity is, okay? It is the slope at a particular point, okay? So you have a function like we had s equals t squared there, all right? And we wanted to figure out the slope at a particular point, and that we would use a tangent line to do that, okay? Now, average rate of change, on the other hand, is the slope between 2 points, okay? So you have 2 points and you're figuring out the slope of that line, and that's called a secant line. So a secant line goes through 2 points, a tangent line touches a graph at 1 point. Okay, so tangent lines are used to find instantaneous rate of changes. So let's look at this a little bit further. Next slide. There we go. Whoops. There we go. All right, let me get rid of this junk. There we go. That's basically what I just said there. Now notice here, this is in this picture you have a bunch of different tangent lines here. And the slope, as you can see, is changing. So it depends on what time you're at along the curve, okay? You would have a different rate of change, okay? Or a different instantaneous velocity if you were dealing with velocity. And so this leads to something called a derivative. A derivative is simply finding that slope of a tangent line, okay? Or finding the instantaneous rate of change, in other words. So you want to be able to associate those words together. Derivative, instantaneous rate of change, tangent line. Okay, so here is a formal definition of derivative for you. All right, so you have a function, okay, f. Okay, now we denote its derivative by using this little tick mark here called a prime, f prime of a. Okay, so the derivative f prime of a, okay, is what we would say instead of saying derivative. F prime of a is equal to the limit as x approaches a. So in other words, you know, if a was, or if x was time, it would be as the time gets really, really close to instantaneous, okay? And this is what is happening to the y values, essentially. You're going from f of x minus f of a, all right? So basically, the derivative is the limit as time approaches 0, if x was time, or as whatever rate of change unit would be approaching 0. So it could be like gallons per foot or something like that, and as feet approaches 0. That was a poor example, but anyhow, it's the x variable there as that approaches 0. Okay, so geometrically, it's the slope of the tangent line. Okay, the instantaneous rate of change, slope of a tangent line, derivative. Those are all synonyms. You want to kind of get that terminology down pat in your brain. All right, some more info. This actually makes it easier to compute. So when you're using the derivative, you generally want to use this formula rather than the previous one, okay? So use this. It's a lot easier to use. H is approaching 0, meaning, you know, the time is getting to be close to 0, okay, in essence here. And this is just a reworked version of that same formula. And I'm not going to show you the algebra to rework it, but trust me, this formula is equivalent to the previous one. Okay, so h is approaching 0, time is getting close to 0. And in terms of x and y, this formula is actually the more kind of useful one. So this is really the one you want to use here, okay? So the limit as h approaches 0, you have a function where you're inputting x plus h into the function minus f of x all over h. Okay, and this allows you to figure out the instantaneous rate of change or the slope of a tangent line, this function right here, okay? So this is the function that we're going to use for calculating the derivative. And the derivative is all what this lesson is about for the most part, other than getting you introduced to what the derivative is. Okay, and so we're going to do a couple examples in the next video. Thanks for watching this one. All right.